Hi class, this is lesson 16, Bayes' theorem, where we'll finally be getting off our posteriors. Bayes' theorem turns out to be an immediate consequence of the law of total probability from the previous lesson. Here's the statement of Bayes' theorem. If A1 through AN form a partition of the sample space S, which we learned a lot about in the last lesson, and if B is any event, then the conditional probability of AJ given B equals, well, by definition of conditional, it's just the probability of the intersection of AJ and B divided by the probability of B. That's just by definition. Here's the theorem. That, in turn, equals the probability of AJ times the conditional of B given AJ over that mess in the denominator. The numerator just follows by definition of conditional. The denominator follows precisely by the law of total probability from the last lesson. The PAJs are known as prior probabilities that we see before B. The PAJBs are posterior probabilities that we calculate after observing B, after receiving that information. Now those posterior probabilities add up to 1, and that's why we have the funny-looking denominator on the right-hand side of the theorem. Let's do a couple examples. Two political candidates are at a debate. Candidate A is asked 60% of the questions, and B is asked just 40% for whatever reason. A is likely to make a stupid answer 20% of the time, and B makes a stupid answer 50% of the time. What a surprise. One of the candidates is asked a question and makes a dumb answer. We want to know what's the probability that it was in candidate A. Now, the answer should be less than 60% since dumb answers favor B. Anyway, you heard a dumb answer is, by Bayes' theorem, the probability of A times the conditional of D given A divided by that same term plus the other term in the partition, probability of B times probability of D given B. Now it's a plug and chug. The probability of A is 60%. That's the unconditional probability. The probability that we see a dumb answer given A is 0.2. Okay? That 0.6 times 0.2 comes down to the denominator, and the other term in the denominator is the probability of B, which is 0.4, 40%, times the probability of D given B, a whopping 50%. When the smoke clears, you get an overall total of 0.375. And so that means that the probability that it was candidate A, given that you saw a dumb answer, that's only 0.375, which I guess is okay because A is supposedly answering 60% of the questions during this debate. So we got enough information that allowed us to change the probability of A from 60% all the way down to 0.375. Notice how the posterior probabilities depend strongly on the priors and the information we received. Here's another famous example. In a certain city with good police, the probability that any defendant brought to trial is guilty is 0.99. So they get their answer right most of the time. On the other hand, the juries are very good. In any trial, the probability that the jury sets a defendant free if he's innocent is 0.95. The probability that they convict if he's guilty is also 0.95. Let's find the probability that the defendant is innocent given that the jury sets him free. So you got the talented cops, you have the talented jury. Let's see which one wins out. So we'll have the events I equals innocent, G equals guilty, or I complement, and F is the event that the jury sets him free. The probability that he's innocent given that he was set free equals, by Bayes' theorem, probability of innocent times probability of being set free given that he's innocent divided by that same term plus the other term in the partition, the probability that he's guilty times the probability that he was set free given that he's guilty. Plug and chug, probability that he's innocent. Cops don't bring in innocent people usually, so that's 0.01, but the jury's good. The probability that he's set free given that he's innocent is 0.95. Take that term down to the bottom and then add in the other term. The probability that he's unconditionally guilty, 0.99. The probability that he's set free given that he's guilty, jury doesn't make mistakes much, that's 0.05. When the smoke clears, the probability that he's innocent given that the jury set him free was 0.161. It's still kind of low, but it's a lot higher than the original probability of 0.01 that he was innocent. Now we'll do another very famous example. You are a contestant at a game show. And this game show is called Let's Make a Deal, actually. Behind one of the 3 doors is a car. Behind the other 2 are goofball prizes like goats. So you pick door number 1. The host of the show, Monty Hall, opens door 2 and reveals a goat. Monty offers you a chance to switch to door 3. What should you do? And I'm going to just say, note that if the car is actually behind your door 1, Monty randomly shows you either door 2 or 3. He knows where the good stuff is. So by Bayes' theorem, we have the probability that the car is behind door 1 given that Monty shows you door 2 equals the following thing. It's a little bit messy because I've kept the English in there. It's simply the probability that Monty shows you door 2 given that the car is behind door 1 times the probability that the car is behind door 1 divided by the law of total probability mess on the bottom. Let's do a plug and chug. The probability that Monty shows you a door 2 given that the car is behind door 1 is 1/2 because he could show you either door 2 or door 3. The probability that the car is behind door 1 is actually 1/3 because we're assuming that they were placed randomly. So take that term down on the bottom, 1/2 times 1/3. Similarly, the probability that Monty shows you door 2, given that the car is behind door 2, that's 0. That's where that 0 comes from. And again, the probability that it's behind door 2 is 1/3. Finally, the probability that Monty shows you door 2, given that the car is behind door 3, well, he's going to show you door 2, no doubt about it. So that probability is 1. And then you multiply again by the probability that the car is behind door 3 is 1/3. When the smoke clears, the answer is 1/3. So the probability that the car is behind door 1, given that Monty shows you door 2, is 1/3. That's the same as the unconditional probability that the car was behind door 1 to begin with. Okay, great. Let's keep that in mind. On the other hand, the probability that the car is behind door 3, given that Monty shows you door 2, now you have been offered the chance to switch to 3. Okay, that thing, blah, 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 by Bayes' theorem, that works out to 2/3. 2/3. And what's critical here is that the probability that Monty shows you door 2, given that the car is behind door 3, is 1. And so by going over from your door 1 to door 3, as Monty has allowed you to do, it's the thing to do. It is prudent to switch. So good move. Let's do that. Now, if you don't quite believe this, you aren't alone. This problem came up in the popular literature in some news articles, and people are just fighting with each other. Even professors were getting the answer wrong. But it turns out what I've shown you is correct. You switch. And if you still don't believe me, think of what you would do if there were 1,000 doors and Monty revealed 998 of them. Of course you'd switch from your door to the remaining one. There's no way that you would have originally chosen the correct one to begin with. Okay, fantastic. So I'm going to leave you with that thought because we are now done. Okay, fantastic. It's been great getting to know you. See you soon.